So up until test one, we were talking about electricity, one of the forces of nature. And now, up until test two, we'll be talking about magnetism, another force of nature. When we talked about electricity, we discovered that actually it's kind of this force that's hidden within matter, because matter's made of electrical charges, and it's actually really a very strong force. We're going to find similar things about magnetism. That magnetism is actually a force that's hidden within inside matter, and magnetism too is a really strong force. Ultimately, we'll discover that electricity and magnetism are related to one another. I mean, they're like kind of a husband and wife, because they had a child, and the child was light. And so that's our plan for the course overall. But right now, let's just say we've met electricity, and now we're going to introduce magnetism. Later on, we'll find they get married and have a child called light. So that's basically the plan. Okay. So today, I want to talk about this list of topics here. I want to introduce magnetic attraction, magnetic repulsion. We'll start with that. I want to introduce magnetic south poles, magnetic north poles as explanations of magnetic attraction and repulsion. I'll then introduce the concept of magnetic fields conveying magnetic forces, like we introduced the concept of electrical fields conveying electrical forces. And I'll end up by discussing what we call the magnetic field equation. It's kind of the parallel to the electric field equation that we met in electricity. Actually, our path here through magnetic attraction, repulsion, magnetic south and north poles, magnetic fields conveying forces, the same sort of path that we took through electricity, where we met, electrical attraction and repulsion. We met positive and negative charges, and we met electrical fields conveying electrical forces. So there's a similar path. There's lots of similarities, but there's also differences on the path. There's differences between electricity and magnetism. Okay, I always like to include a little bit of history. I know that's extremely popular. So as you know, the first documentation of the electrical force, or electricity, goes back to those ancient Greeks in Athens or wherever they lived. And amber, this material amber that was used in jewelry, and they rubbed to polish the amber, and they found that it attracted things like hair and straw and other light materials. Those ancient Greeks from Athens and wherever, they also documented, they were the first to document magnetism. So they observed, or they found, they discovered materials, once magnetite, that would attract and repel one another. And we now understand that as magnetism. So we have to thank the ancient Greeks for both the first documentation of electricity and the first documentation of magnetism. So we now understand, of course, that the explanation of the rubbed amber attracting hair, straw, or wool was the fact that there's an electrical force, and in materials there's electrical charges that are exerting electrical forces. We now also understand, have a similar explanation for the magnetic effects that the Greeks documented. So there's similarly, there's a magnetic force, and inside materials there's moving charges, which are the sources of magnetic forces, magnetic interactions. And so the discovery and documentation of electricity and magnetism, both cases opened us up to this world that inside matter, there's kind of this electrical and magnetic world of charges and moving charges that are exerting electric and magnetic forces. So there's a huge breakthrough. Okay, so why is magnetism important? There's lots of reasons magnetism is important. I'll mention a couple of them. I just got to remind myself. Yeah, this is the one I wanted to remember here. You know, nowadays it's important because all the data that we're storing, you know, on, I guess, Facebook, you probably don't use. My daughter told me that. But all these other sites like Instagram and Twitter and TikTok, all this data, all these masses of data are being stored magnetically. They're being stored by magnetic bits that say zeros and ones. And so that's how we store data. And it's massive, massive amounts of data that is stored today. So it's very important in our everyday lives. It's also true that magnetism has saved our lives because the Earth is exposed to cosmic radiation from outer space, and the magnetic field of the Earth is kind of a shield from that, an umbrella that protects us from that cosmic radiation. So without the Earth's magnetic field, there would be no life as we know it on Earth, because the radiation, the cosmic radiation on Earth would be too large for us to survive. Only cockroaches would survive those conditions. So we have to thank magnetism for that as well. So magnetism also has a big scientific importance. Not just saved our lives, but it has and stores our data, but it has a big scientific importance. And that scientific importance, we think, is it was the second great unification in physics history. So the first great unification in physics history, you met in Physics 211. The first great unification is the joining together in one theory terrestrial motion, say of a basketball or a football, and celestial motion, the motion of the moon or the Earth around the sun or the sun in the galaxy. Those two motions were, the celestial and terrestrial motions, were joined together in one complete theory by Isaac Newton. That was the law of gravity. So that was a huge breakthrough, and it's the first great unification in physics. The second great unification in physics is the unification of electricity, which we were talking about up to test one, with magnetism that we're going to start talking about now, and we'll lead on to test two. So this was the second great unification in physics. It's a more recent one. You know, it's due to James Clerk Maxwell, not due to Isaac Newton. James Clerk Maxwell was born 100 years later after Newton died, but Maxwell's time was the time of electricity and magnetism, like Newton's time was the time of terrestrial and celestial motion. Okay, so let's talk about magnetic attraction and repulsion, and we're going to talk about it by comparing it to electrical attraction and repulsion. And specifically, we're going to talk about magnetic poles, north and south poles, and we're going to compare those to electrical charges, positive and negative electrical charges. And we're going to see a lot of similarities, although there are some differences. So I want to show you, I'm going to put the video on, I think, the camera on. So if you look in the center of the screen here, I've got this is a magnet. So this is a piece of iron that's magnetized. And I've indicated on the magnet in red, that's what we call the north pole. So that's one end of the magnet. And in blue here, this is the south pole, the other end of the magnet. And then I've got a second magnet, this one here, that's also got a north pole marked in red and a south pole that's marked in blue. Just like unlike charges, a positive and negative, attract one another, and like charges repel one another, two positives repel, two negatives repel. Unlike poles, magnetic poles, they attract one another, and like poles repel one another. So a north pole and a south pole, a magnetic north and south pole, will attract one another. A pair of north poles will repel one another, and a pair of south poles will repel one another. So I just want to show you this on the video. This magnet is on a turntable that will rotate. If I bring my north pole in my hand, if I bring it up towards the north, oh look, already it's starting to move. You're seeing the magnetic repulsion. And so that's an example of magnetic repulsion between the north pole and the south pole. If I bring up the south pole, now I'm going to bring up the blue end of the magnet. So this is opposite poles. And now I get attraction between the opposite poles. And so that's magnetic attraction between a north pole and a south pole. Let me just show you the case of, just to prove it, two south poles. So again, this will be two like poles. So I'm going to bring the south pole up to the other south pole. And again, I get repulsion. And so think about how similar that looks to electricity. There, in electricity, we have positive and negative charges. With like charges repelling one another, we had unlike charges attracting one another. We've got the same sort of thing here. We've got unlike poles attracting one another, a north and a south pole, and then we've got like poles repelling one another. Two north poles or two south poles repel one another. Those repulsions and attractions, whether they're electrical or whether they're magnetic, are actually due to the charged constituents inside the matter that we're seeing attract and repel. So it's a glimpse at the nature of matter. It's actually a glimpse at the electromagnetic nature of matter. And specifically, what we're about to discover, remember, it's charges that cause the electrical force. It's the moving charges in matter that cause the magnetic forces. So you can see there that there must be some deeper connection between electricity and magnetism. Electrical charges are causing electrical attractions and repulsions between matter. Moving electrical charges inside matter are causing the magnetic attractions and repulsions between matter. Okay. Those interactions that I just showed you between the bar magnets, I mean, they're amazing to see when you think about it, because those are actions at a distance. Through that space, that basically empty space between the poles, there was an attraction and a repulsion. And we now understand that attraction, repulsion through empty space as being transmitted, mediated by a quantity that we call field. Electrical fields in electrical case, it's magnetic fields in magnetic case. So I want to talk about magnetic fields, the properties, characteristics of magnetic fields. I want to compare them to electrical fields, the properties and characteristics of electrical fields. So let's do that. On this slide here, I'm comparing the electrical field upstairs on the left here of an arrangement of charges with the magnetic field downstairs here of a bar magnet with a north and a south pole. So this guy upstairs is sort of a reminder from before test 1, and this is an introduction to new material for test 2. This arrangement here is an important arrangement. It's the electrical field of an electrical dipole that's made from a single positive charge and a single negative charge. This is a kind of magnetic equivalent of that. This is an important arrangement of magnetic field. It's a magnetic field that's made from a simple arrangement of a north pole and a south pole on a bar magnet. So you got a positive charge and a negative charge. You got a north pole and a south pole. The same type of magnetic versus electrical arrangement. The upper one is what we call electric dipole. The lower one is what we call a magnetic dipole, to stress their similarities. They're both dipoles. They both have opposite charges or opposite poles. The field lines up here, these electrical field lines we've met before, we know how to read these, right? If the field lines are closely packed together, like in this region here, that's strong electrical field, and near the charges, strong electrical field. If the field lines are loosely packed together outside here, that's weak electrical field. So they tell us the strength, the size, magnitude of the electrical field. They also tell us the direction. Along this midplane, right, the field is going from left to right, because the field lines are going from left to right. Near the positive charge, the field lines come radially outwards. That's the direction of the field near the positive charge. Near the negative charge, the field lines are going radially inwards. That's the direction in the location of the negative charge. Same ideas for the magnetic field. So where the field lines are packed closely together, that's a region of strong magnetic field. Where the field lines in green here are packed loosely together, that's a region of weaker magnetic field. If you look in the magnet itself, you see these field lines are closely packed. So the field's strong in the magnet and near the North Pole and near the South Pole. The field is much weaker far from the magnet, especially to the left and right, upstairs and downstairs here to the magnet. So you can read off again the magnetic field strength or magnitude or size from this field line diagram. The lines also tell you the direction of the magnetic field. So if you look at the North Pole, the field lines are coming out, emerging at the end of the North Pole. And that's a characteristic of North Poles. So every bar magnet with every North Pole has field lines coming out of the North Pole. South Pole, the field lines appear to head into the South Pole of the bar magnet. And that's true of every bar magnet. Every bar magnet has a South Pole, and the field lines are heading into that end of the South Pole. And in between, right, you see all the field lines emerging from the North Pole and returning to the South Pole. You see that upstairs here, you see it downstairs here. So in this plane, midway between the North and South Pole, the field is actually from the left to the right. So everything that we learn about field lines for electrical fields, how to read the field lines, the sizes of the fields, the directions of the fields, how to draw the fields, all that applies to magnetic fields. There's nothing new to learn. The same way to read the size of the magnetic fields, same way to read the direction of the magnetic fields, same story for drawing or mapping out magnetic field lines. The most important difference on this slide between the two, and there is a difference, it's like a where is Waldo thing. The difference is that if you look at the upper slide for the electric field lines, they have ends to them. So they begin on the positive charge. They emerge from the positive charge, and they end on the negative charge. So they have beginnings and ends. But if you look at the magnetic case, the magnetic field lines don't have beginnings and ends. They just form loops. So yes, they do come out of the North Pole and they do head back into the South Pole. But inside the magnet between the South Pole and the North Pole, you see the field lines streaming along the magnet from the right to the left, from the South Pole to the North Pole. So all the field lines down here are loops. I tried to show that, not very well with these lines here. They all form loops. There's no endings of the field lines for the magnetic case. They don't form loops upstairs here for the electrical case. They come out of the positive charge and they return to the negative charge. So there is a difference. Okay, I wanted to show you the Earth's magnetic field, mention a few interesting things about the Earth's magnetic field. We've already said that it did save our lives, so that's kind of interesting. Where does it come from? You probably know where it comes from, that at the core, inside the Earth, right near at the core, there's molten iron. And that molten iron's rotation is creating this magnetic field. So just like my bar magnets are iron, at the center of the Earth is a massive, massive amount of iron that's rotating. It's liquid, it's hot, it's rotating. That's making this magnetic field. So that's where the magnetic field comes from. A few interesting facts about it is, one fact is that the magnetic North Pole, where the field lines come out of, where's that located? It's actually located at the geographic South Pole. It's located in Antarctica. The magnetic South Pole, where the field lines head back into, where's that located? That's actually located in Canada, somewhere up in the Arctic Circle. So the magnetic North and South Poles are reversed from the geographic North and South Poles. So that's kind of interesting. And it's actually interesting that over the history of the Earth, they have flipped backwards and forwards, like they can't make up their mind. Sometimes they were pointing, this is every 100,000 years, so they stay with their decision for a while, but they flipped from North Pole of magnetism being North Pole of geographic North Pole to reversing, and they reverse back and then reverse back again. And they've done that a number of times over the lifespan of the Earth. Also, the North Pole isn't the magnetic South Pole isn't exactly located at the geographic North Pole. It's not exactly at the North Pole. It's some degrees off. Right now it's about 11 degrees off, so it's actually in Canada. And it wanders around. It moves around. And so the magnetic North and South Poles are not perfectly stable. They have flipped over the history of the Earth, and they do wander around over Canada and Greenland and so forth. So they have been wandering around. So those are all interesting facts. There's lots of things we don't understand about why that's happening. On this plot here, or on this diagram here, you see the South Pole is up, magnetic South Pole is near the geographic North Pole. You see that it's displaced, comes out in Canada, 11 degrees right now from the geographic North Pole. And you see here the field, the pattern of field lines that is created by the Earth's magnetic field. So again, remember the rules that the field lines come out of the North Pole. So you see them coming out of Antarctica or Chile or what else is down here? I don't know any geography. Argentina, somewhere there. They're pouring out of the bottom of the Earth. Not a good term. And then they're heading back into the top of the Earth up here, into Canada. And so that's the pattern of field. If you were upstairs in Alaska, then the field lines would basically be roaring straight into the ground, vertically almost. If you were downstairs here in Chile, they would be roaring out of the ground, vertically upwards. If you were on the equator, they'd be traveling sort of horizontally across the room. And so that's the pattern of field lines. I can try and show you a little demonstration of that with this. I have the Earth here, conveniently. And this Earth is also a magnetic Earth. And here I've got a compass needle that I can probe the magnetic field. So up here's the north, this is geographic North Pole, and downstairs here's the geographic South Pole. Let me say what I mean by that. It's the poles about which the Earth rotates. That's what we mean by geographic North and South Pole. The Earth is rotating, and it's about those poles, about those points. This is the approximate location of the magnetic South Pole. There's a little S here. And downstairs here, this is the location of the magnetic North Pole. So the field lines are coming out at the bottom and heading in at the top. So let me put this little compass needle down here. And what you see is that the field, it's pointing in the direction of the field lines, and it's sort of pointing out of the Earth. So this is where the field is coming out of the Earth. And then if I walk up through Australia, always wanted to go there actually, and then through whatever this place is, I come up to the equator, and look, around the equator, the field line is now approximately kind of to the level of this demonstration, parallel to the surface of the Earth. Should be a bit closer. And then if we go further up, I can't see anything because my hand's in the way. The field lines are now really pointing straight into the Earth, right? And so if we were able to take that field trip from the geographic North Pole, we'd see the field lines going in. We'd see them sort of run parallel to the surface of the Earth near the equator, and then come out down near Antarctica. Okay. I want to show you another demonstration in which we're going to use iron filings as little compass needles to map out patterns of magnetic field. Now, iron filings will line up with the direction of the magnetic field. And iron filings will move to where the field is strong and away from where the field is weak. So if you scatter iron filings around a magnet, what you'll discover is that you'll get regions where there's lots of iron filings collecting together. That's the strong magnetic field region. You get other regions where there's not many iron filings because the field is weaker. And you'll see them turned or orientated along the direction of the magnetic field. So we're going to look at that on this thing here. Okay, so this has got like canola oil or some sort of oil in this little box here. And in that oil is lots of iron filings. And so if I just stick it on here, it just looks like this, kind of uniform distribution of iron filings. Now, I've got a magnet here. It's a very small bar magnet. You probably can't see it very clearly. There's a red end of North Pole and a black end of South Pole. And I can put this inside this box. This is why this box didn't cost $5. It cost like $500. It's because it's got that little hole inside it. But look, this is fascinating. Look at those iron filings mapping out for us in real time the magnetic field. So here's a pole, and here's a pole. The magnetic filings are collecting near the two poles because the field is strong there. And you see this pattern of field lines from one pole to the other pole. You see these curves of the field lines downstairs here, the curves of the field lines upstairs here, the field lines radiating outwards on the far right, the field lines radiating outwards on the far left. So that's the iron filings literally imaging for us. I could watch this all day, and sometimes I do. Yeah.
So what's better, the electric field line therapy or the magnetic field line therapy?
What's better? Now you're really asking an expert on that. I have, okay, so electric field therapy. The only electric field therapy I knew was electric shock therapy that they did in the 1960s, and I don't think we do that anymore. So, I mean, maybe we do it a little bit, but magnetic fields. So there is a technique, transcranial magnetic resonance or something. It's not really that, but I made it up. That you can use to excite regions of the brain if you have, for example, in treating depression. Now, I'm getting completely off track here. But so I don't know in general what's better therapy, but I know there's a real, I guess I know there's a real magnetic therapy that's used in medicine. And I don't know about electricity anymore, where we still shock people. Okay. But this is a real imaging of the magnetic field. It's really an amazing thing. If you put two magnets together, we said that if the two north poles are put next to one another, that will create an attraction. And actually, you can see that, that will create a repulsion, sorry. You can see that repulsion in the field lines because the field lines will push themselves apart. If you put a north pole and a south pole together, that's where you get magnetic attraction. And in the case of the field lines, you see the field lines attracting one another. They will leap from the north pole to the south pole. So I want to show you that because we actually bought two of these things to do that. So I'm going to put both of these on this arrangement in this way here. And then I'm going to put a magnet. Where is the other magnet, though? Oh, thank you. You saved me. I'm going to put, so the red end is up here in this one. The red end is upwards in this one. And so I'm going to put them together like this. This will be two north poles together. And so let's take a look at that pattern. So again, here's a north pole. Here's a north pole. On the far left is a south pole. Far right is a south pole. Field lines curl from the north pole of a magnet to its south pole. We're seeing that downstairs here and upstairs here. Also over here, from the north pole to the south pole and upstairs, the field lines are curling around. But you see, look at these field lines here. Look at them here. Look at them upstairs here. Upstairs here. You can imagine them being pushed apart from one another because those two magnets are being literally pushed apart from one another. So you see the field lines repelling each other. You'll see that more clearly when I show you the case of putting the north and south pole together, where you see them attract one another. But here they're really pushing each other, or pushing away from each other. Okay. So I'm going to shake up the two magnets again. Where did it go? Shake up the two iron filings again. And then this time I'm going to put north pole up in this one, and I'm going to put south pole up in this one. And we'll put those back on. So again, here's a north pole, and here this time is a south pole. And these attract one another. At the far end of the magnet with the north pole in the middle, there's a south pole. And at the far end of the magnet with the south pole in the middle, there's a north pole over here. So in both cases, you see field lines that are going from the north pole around to the south pole of the magnet. But if we wait long enough, come on. These field lines in this region here near the center for the right-hand magnet, these ones in this region here near the center for the left-hand magnet, they're not being pushed apart anymore. They're being attracted to the opposite pole. So you see them curling towards the opposite pole. And so this is the case of an attraction between the two magnets. Anyway, I wanted to show you that. Here are pictures of the same situation. So this is just a magnet, north pole, south pole, strong magnetic field, field lines that are emerging from the north pole and ultimately return to the south pole. this is the case of two north poles facing off against one another. So here's where you get magnetic repulsion between like poles, and you see that the field lines are curling away from each other. These ones from the bottom magnet curl away to the left, curl away to the right, as they're kind of repelled by the upper magnet. The ones emerging from the north pole of the upper magnet curl away to the left, curl away to the right from the other north pole. So this is magnetic repulsion. And then finally, the case we're looking at here, this is magnetic attraction. Now we've got a north pole and a south pole. These two poles attract one another because they're unlike poles. And you see the field lines that emerge from the north pole are actually being collected by the south pole up here. So they are not repelled away to the left and right, rather they're attracted to the other pole. And so that's just demonstrating with iron filings these patterns of field lines. What did I do? I'm like coming apart. As long as my head doesn't fall off, I guess. Okay, now I'm completely disorientated. I did want to make this point again, that there is this major difference between the electrical field and the magnetic field, and it has to do with the existence of electrical flux and the absence of magnetic flux. So, as I mentioned, field lines emerge, electric field lines emerge from positive charges, and they end on negative charges. And so the positive charges we can think of as source of electric flux and kind of the sink, the drain of electrical flux, depending on whether they're positive or negative charges. That's not true in the magnetic case. In the magnetic case, there are no isolated north and south poles. They always come in pairs. The magnetic field lines don't suddenly emerge from a north pole or terminate on a south pole. Rather, the magnetic field lines always form loops. So there's no such thing as this in magnetism. There's no beginnings or ends of magnetic field lines. They're always in loops. Okay. Well, we haven't had any equations up to now, so we better change that, I guess. We're going to introduce a new equation. We're going to introduce it by comparison to an old equation. We're going to introduce the magnetic field equation. So it's the equation that tells us exactly how the field influences, magnetic field influences a moving charged particle. And it's analogous to the electrical field equation, which tells us exactly how the electrical field influences an electrically charged particle. And so that's what we call the field equation. So this has got a lot of words on it, but let me just walk through this slide slowly. Upstairs here is just so in magenta, or whatever this color really is meant to be a reminder. There's two field equations you've already met. One of them, we didn't call it a field equation, I think, in Physics 211, and the second one in the first third of Physics 213. So it's the field equation for the gravitational force and the field equation for the electrical force. So the field equation for the electrical force is this guy here, F equals QE. It's the equation that says if you put a charge in an electrical field, the force that it experiences is the product of the charge, Q, and the field E at the charge's location. So that's the field equation. And that's the equation that's telling us quantitatively exactly how fields convey forces. The gravitational version is the equation here that says if you put a mass in a gravitational field, say the Earth, then it experiences a gravitational force, and that gravitational force is equal to the product of the mass that's experiencing the force times the gravitational field that you've immersed it in, so mg. So mg, You didn't know it. All that time you were using it in Physics 211. That's a field equation. Tells you how gravity works through the gravitational field. And so those are two field equations we're happy, we're familiar with, we know and love them or whatever. Let me say a few general remarks about those field equations. So that's now moving on to the text in red. As I say, they're the guys that describe how the field works in mediating, conveying, carrying, can't think of any more of those type of words, transferring the magnetic force, the gravitational electrical force between masses or charges. So they tell us how the forces convey, the fields convey the forces. If you look at the structure, what I would call the structure of those equations upstairs here, they have the form of a vector, which is the force, equaling another vector, which are the fields, times a scalar, which are the masses or the charges. So they both have that form. Because they both have that form, that the force vector is equal to the field vector times a scalar, which is the mass or the charge, the forces are what we call collinear with the fields. Now, collinear is just a word, a technical word, that means either the force is in the same direction as the field, or they're in the opposite direction as the field. They're along the line that's defined by the field. In gravity, it's very simple, because gravity's, the masses are always positive, and so the force and the field are in the same direction. In electricity, it's a little bit more complicated, because you've got positive and negative charges. They're plus and minus signs. The forces can be in the direction of the field or opposite the direction of the field, and that's what we mean by collinear. That's just what that word means. This is where the field equation for magnetism, so the equation that describes the relationship between magnetic force and magnetic field for magnetism, differs from the field equations for electricity, field equations for gravity. And so that's these last two bullets here. The field equation for magnetism also has this form where the force, the magnetic force, is the product, equal to the product of the field that carries the force, times some property of nature. But this time, that property of nature is not a scalar. It's not like mass, that's a scalar. It's not like charge, that's a scalar. It's actually a vector property of nature. It's the product of the charge's charge and the charge's motion, the charge's velocity. So that product, I wrote it as QV, that product, that property of that moving charge is a vector quantity. And so there's a big difference here for the field equation for magnetism versus the field equation for electricity and the field equation for gravity. In the former cases, it's a scalar times a vector field that gives the vector force. In the latter case of magnetism, it's a vector property, charge times velocity, times the field, that gives the magnetic force. And so that's a big difference. So we're going to see that in the field equation. On the next slide, I'm writing down the field equation. Okay, so here's the old friend field equation for electricity. Electrical force on the left equals the electrical field on the right times the charge. And as we say, if we want to think about the direction, it's either parallel or opposite, anti-parallel. The force is parallel or opposite the electrical field, because the charges can be positive or negative. Here's the field equation for magnetism. So this is the new equation. We're going to be working with this equation. This tells you the magnetic force. That's over here on the left-hand side of the equal sign, just like upstairs here. This told you the electrical force. And it's the product of the field. So here was the electrical field. B is the magnetic field. That's the symbol we give the magnetic field. And that E, or that E was multiplied by charge. Charge was the property experiencing the field and feeling the force. Here, QV, that's the property that's experiencing the magnetic force. is the product of the charge and the motion of the charge. And then finally, there's this sine theta factor. And that has to do with the fact that both B has a direction and QV has a direction. The velocity has a direction, the magnetic field has a direction. And this is the sine of the angle between those two directions. And this force's direction is actually perpendicular to those two directions. So that's much more complicated. Both these field equations are about imagining kind of probing the magnetic or electric fields. In one case, you probe it by placing a charge in the field and experiencing the electrical force. That allows you to kind of see the electric field. The other case is where you imagine putting a moving charge as the probe of the magnetic field. Put a moving charge in the magnetic field. It'll experience a magnetic force. That's how we see the magnetic force. So these field equations are how we define electric magnetic fields, are how we explore electric magnetic fields. Now we've got to go on and look at the details of this magnetic field equation. Okay. So the first thing I said was that the direction of the magnetic force is actually perpendicular, right angles, 90 degrees, to the direction of those two other vector quantities, the magnetic field vector and the velocity vector. So it's right angles to those two. It's 90 degrees to those two other vectors. And that's shown here. So if you look at this plot, B is the magnetic field in green. V is the velocity vector in red. These are the two vectors on the right-hand side of the field equation. And theta here, this is important, theta is the angle between those two ingredients that determine the magnetic force. So it's the angle between the direction of the velocity vector and the direction of the magnetic field. Then the force itself is at right angles to the plane that's defined by these two vectors. So imagine these two vectors here. They define this rectangular plane. They lie in this rectangular plane. And the force vector will be perpendicular to those two. There's a couple of interesting special cases about magnetic forces I want to mention. So one is, if you remember the field equation, it says that magnetic force is Q, V, B, sine theta. And theta is this angle between the direction of the velocity vector and the magnetic field vector. If V and B, if those two vectors are perpendicular to one another, if they're at right angles to one another, if V and B have 90 degrees between each other, what does that mean? That means that sine theta, sine 90, will be 1. That's when you get the strongest, the largest magnetic force, when you make the angle between V and B 90 degrees. That'll make the biggest magnetic force. The other extreme is if V and B are parallel to one another. If V and B are in the same direction, that is that the angle theta is 0 degrees, then the field equation tells you that the force will be proportional to sine theta, sine 0 degrees. Sine of 0 degrees is 0. So if V and B are in the same direction, there's actually no magnetic force. The force vanishes. So this is way stranger than electrical forces in electrical fields, because now the direction of motion of the charge through the field has an effect on the strength of the force. If the direction is motion at right angles to the field, you're going to get a big force. If the direction of motion is either parallel or actually also opposite, theta's 180 degrees, then you get no force. So it's a really weird circumstance where you can change the direction of the particle in the magnetic field. You change the strength of the force, magnetic force on the particle in the magnetic field. And you can even make it go away if you have the particle going parallel to the field lines or opposite the field lines. How do you find the direction of the how do you find the direction of the force? Well, we do that with a recipe or a rule that's called right-hand rule. So right-hand rule is a recipe rule that tells you how to find the direction of the magnetic force from the direction of the motion of the charged particle and the direction of the magnetic field. So let me show you how you can do the right-hand rule. So first of all, you do want to use your right hand for the right-hand rule. Okay? So here's my right hand, and on the right-hand side of the field equation, there's two vectors, remember. There's the velocity vector, and that's the first one in the equation, and then there's the magnetic field vector. You point the palm of your right hand in the direction of the velocity vector. So in this case, I'm pointing my hand towards you as if the motion of a moving charged particle is towards you. You curl your fingers of your right hand in the direction of the magnetic field. So if I curl them this way, it would be that the magnetic field line is going from left to right across the room. Your thumb, there's only one way you can curl your fingers, right, without pain. So you curl your fingers in the direction they will curl, in the direction of the magnetic field. Your thumb then, again, will naturally point in one direction. That will be the direction of the magnetic force. And so that's the right-hand rule. And we're going to get some practice in using that. So again, palm of hand in direction of the velocity. That's the first vector in the field equation on the right-hand side. Curl your fingers in the direction of the magnetic field. That's the second vector in the field equation on the right-hand side. Your thumb naturally points in the direction of the magnetic force. This would be the direction of the magnetic force. If a charged particle was moving towards you, the field was heading left to right, the force would be up. Let me qualify that. That's the case for a positive particle. So this right-hand rule tells you the direction of the force on a positive particle. If it was a negative particle, the direction of the force is opposite the thumb. Just like a negative charge in an electrical field, the direction is opposite the field. If you've got a negative charge, it's opposite where you're right. So we use the right-hand rule for the negative charge, but then we just say, oh, it's negative. I'm going to point it in the other way at the end. Okay. Here's a couple of examples. Let's see if we can do these. In this overhead, I've got a magnetic field that's from the left of the room, over here, to the right of the room. I've got two moving charged particles. There's a positive one, and it's heading straight upwards towards the roof from the floor. And I've got a negative one. It's heading straight upwards to the roof from the floor. And so these are both, this is the ingredients for a magnetic force, right? We've got moving charged particles in magnetic fields, and we can figure out the directions of the forces on the positive and negative charged particles using our right-hand rule. So let's try and do this. Again, I'm going to start with the velocity vector. That's the first vector on the right-hand side of the field equation. And the velocity of the charged particles is upwards. I'm going to curl my fingers in the direction of the magnetic field. The magnetic field lines on that slide are from the left of the room to the right of the room. So I'm curling my fingers from left to right. My thumb points in towards the screen. That means that the force on a particle, positive particle that's moving upwards in a field that's towards the left is in towards the screen. And so if we look on this slide, that's the direction that this force arrow is pointing in. That's the direction of the force on this positive charged particle. It's in towards the screen. For the negative charged particle, it's moving upwards, so it's still palm of the hand upwards. It's in the field that goes left to right, so fingers still point from left to right. My thumb still points in towards the screen, but we say, aha, this is a negative charge particle, and so the force on it is actually opposite this thumb's direction. So it's out of the screen towards you. And so the negative charge particle is being forced out of the screen towards you. You see the positive charge particle under this force, under this influence, is being curled in towards the screen. The negative one, under this force, under this influence, is being curled out of the screen towards you. Okay. So where have I got to? Good question. We talked about magnetic attraction repulsion. We talked about magnetic poles, like poles, unlike poles, as causes of attraction and repulsion. We've now talked about fields as mediating, carrying that attraction and repulsion. We talked about how to draw fields with field lines, just like electricity. And we've talked about the field equation for magnetism versus the field equation for electricity. The field equation for magnetism is fundamentally different in that the property experiencing the field is a vector thing. It's charge times velocity. The property experienced in an electrical field is a scalar thing. It was just charge. That makes this field equation for magnetism more complicated. Sorry about that, but it's real. The electrical case we're now appreciating was a rather simple case. It was a simple field equation. So I've got some examples now of working with the field equation. Okay, so here's some more right-hand rule examples. And we've got, I'm going to go through 3 or 4 of these. We've got 4 different situations: top left, top right, bottom left, bottom right. The charged particles' motion are shown by the little red arrows. So, for example, this charge here is moving towards the right, this one's moving towards the left, this one's towards the left, this one's up. The charges can be positive or negative. In this case, we've got 3 red or orange-colored positive charges and 1 blueberry-colored charge here, negative one. And then the fields are shown by field line sketches. Now, let me just say that often when we draw fields for magnetism, this happens much more for magnetism than fields for electricity, we have fields that are coming out of the screen towards you or into the screen away from you. So how do I draw a field that's coming out of the screen towards you, or a field that's going into the screen away from you? We do it with dots and crosses. So this field here, these crosses, are representing a field that's heading in towards the screen. And I don't have an example here, but we'll see it later, I think. If we had dots here, or circles here, that would be a field coming out of the screen towards you. And so that's something that is a bit new for magnetism. I don't think we meet it much in electricity. We have fields that come into and out of the screen. And this is our language, our convention for how we indicate into the screen with crosses, out of the screen with dots or circles. The rest of the case is, there's a magnetic field here that's heading upwards because the field lines are heading upwards. These field lines head from left to right. These field lines are heading at 45 degrees, somewhat upwards and somewhat towards the right. Okay. So let's see if we can apply. Here are the answers, but let's work through these answers. Let's see if we can apply our right-hand rule to these cases. I'm going to start with the top left here. So in this case, we've got positive charge, and it's moving from the left to the right. So I'm going to point the palm of my hand from the left to the right. That's the direction of motion. My fingers are going to curl in the direction of the magnetic field. So my fingers are curling into the screen because the crosses mean the magnetic field's going into the screen. My thumb is pointing upwards. that means that the force on a positive charged particle that's moving left to right in a field that's into the screen will be upwards. And this is a positive charge, and so this is the direction of the force from right-hand rule in this case. Let's jump over here. So in the case on the top right, let's think about that case. So we got motion here that is from the right to the left. So this time I'm going to point the palm of my hand from the right towards the left. The field in this case is upwards. So I want to curl my fingers upwards. Well, that means I've got to do this. You know, I could have pointed my palm of my hand this way. That's also right to left, and just curled my fingers up like this. And now my thumb is pointing in towards the screen. That would be the direction of the force on a positive charged particle, be in towards the screen. But this isn't a positive charged particle. This is a negative charged particle, so the force is in the opposite direction. The force is towards you. And so I've indicated that that force is directed towards you on this negative charged particle with this dot here. That's our convention. So this means a force that's coming out of the screen towards you. Let's go downstairs here. This is an interesting case. This is a case where we've actually got a motion of a charged particle that's from the right to the left. And we got a field that's in the opposite direction from the left to the right. Here I actually don't really need to use, and it wouldn't be very helpful to use, the right-hand rule. Here all I've got to do is remember that there's a special case in magnetism. If the charged particle is moving in the direction of the field lines, or the charged particle is moving opposite the direction of the field lines, there's simply no magnetic force. It's an amazing thing that if a charged particle it can move through a magnetic field, but if it moves along the field lines, or it moves opposite the field lines, it's as if that field wasn't there. It experiences no magnetic force, a remarkable thing. And so this is a case, because the motion is opposite the field, or if the motion had been the same direction of the field, there is actually no force whatsoever. So I just wrote F equals 0. Final case. It's this one here. So this has now got a field that's at 45 degrees. It's a bit up and it's a bit towards the right. So let's see if we can do this one. This is, I think, one to kind of, like play games with you, as if you can't figure out how to put your hand in this position. But you can do it, right? Except if you stand up here and try and show everybody else. Then it becomes harder. But so the motion is upwards. So I'm going to put my right hand upwards. That could be this way round. It could be this way round. They're all up, or this way round. They're all up right now. And then I've got to point my fingers in the direction of the field. Well, it doesn't seem so hard. I just point them over here. That is the direction of the field. It's partially up and partially towards the right. My thumb then points in the direction of the force on a charged particle with that upwards motion in that 45-degree directed field. And so my thumb is pointing in towards the screen. That is the direction of the force on that positive charged particle. So that is what I've denoted here. This is a force that's in towards the screen on this charged particle. And so those are 4 examples, 4 illustrations of working with right-hand rule. Okay, I've got a quiz here. Let's do this. So in this is another right-hand rule question. In this one, we're told the electron is in the is moving upwards from the bottom of the screen to the top of the screen. The magnetic field is directed from the left to the right, and we've got to figure out the direction of the force on the negatively charged electron. So I'll give you a minute to think about that. I'm going to just play around with the right-hand rule a bit so I know the answer myself. Okay, I'll move on because I'm panicking about, I got one more example I wanted to do and I want to somehow cram it in no matter how fast I go. In this case, let me just say, normally I just forget about, to begin with, whether this is positive or negative charge. I'm just going to worry about that right at the end. To begin with, I'm just thinking about motion and field. The electron is moving upwards. So I'm going to point the palm of my hand upwards. The field is from the left to the right. So my fingers point from the left to the right. My thumb is pointing in towards the screen. That would be the force on a proton, positive charge. This is an electron, negative charge. So the force on this electron is out of the screen. So out of the screen is the correct answer. Okay. Let's look at one last example, which is a quantitative example of the field equations. So we've mentioned that there's three field equations: gravity, electricity, and magnetism. Gravity and electricity are simpler. Magnetism is more complicated because the property that experiences magnetic fields is a vector, whereas the property experiencing gravitational fields and electric fields were scalars. In this particular example, we're told that we went to the equator for this one. This is not working. Okay. We've gone to the equator, and we're at the equator, and we're told that the Earth's magnetic field is 50 microteslas and is pointing north at the equator. We're told that there's an electrical field at the equator in the atmosphere, and that's 100 newtons per coulomb, electrical field, and that's pointing downwards. And based on that information, we're asked to calculate the gravitational, magnetic, and electric forces, so three forces, on an electron that's moving eastward at the equator and traveling at 6 million meters per second. So that's the problem here. I tried to sketch that above the text. So in this sketch, let me explain this. I've imagined north is to the right. So I'm standing at the equator, so imagine kind of standing like this, and north is over there, and east is pointing out of the screen here. So this is my coordinate system that I used when I drew these patterns of field lines. The magnetic field is towards the north, so in green are the magnetic field lines. The electrical field is downwards, so in blue are the electrical field lines. And then red, I drew the gravitational field. That's also downwards, and so in red is the gravitational field line. So the The blue, the green, the red lines are the three fields. Then I drew the moving charged particle. So here's the moving charged particle. It's heading east, so it's coming out of the screen in the easterly direction. And that's what I kind of denoted by this dot here. Its speed is 6 million meters per second, and here's its charge, and here's its mass. And on this overhead here, in this picture here, in this sketch here, are all the ingredients that we need to solve this problem, to solve the gravitational, the electric, and the magnetic forces. So let me do that. So let's first find the gravitational force. We've got an electron, this dot here, in a gravitational field. That's the arrow here. The direction of the force on that electron with some mass is given by the field equation, mass times acceleration of gravity. It will be in the same direction as the field. So that's the direction of that force. The size of the force... Oh, you can't see me? Okay. Size of the gravitational force. It's just mg. And I'm not going to write down the numbers. I've got to do this in like 30 seconds. So I multiplied the mass of the electron, 9 times 10 to the minus 31, times the acceleration of gravity, 9.8 meters per second squared. That is equal to, it's about 9 times 10 to the minus 30 newtons. Electrical force. Electrical field is down. It's experienced by the charge. But since the charge is negative, the force, let me draw another arrow, the force of electricity is actually upwards. So that's the upwards direction of the electrical force. If I want the size of the electrical force, it's just Q times E. I'm just worrying about the size, so I'm multiplying the size of the charge times the size of the field. It's 100 newtons per coulomb times the charge of an electron, 1.6 times 10 to the minus 19 coulombs. That gives you 1.6 times 10 to the minus 18. No, 17, because 100 newtons per coulomb. Newtons.